Hello, welcome back to Cracking the Cryptic, and today a puzzle by James Sinclair, who is a wonderful constructor. And this one is called Double Entendre. Double Entendre is a cryptic clue style in which the same clue can rather brilliantly lead to two totally different solutions, and you would think that was either impossible or an extraordinary fluke that could only happen once in a blue moon. Well, that's what I would think. But in fact, a couple of people have created full puzzles of that style, which is amazing, including Colin Thomas, aka Twin. I think we've featured it on Patreon in the past. And that reminds me, go to Patreon for lots of crossword content. At the moment, the latest thing is Simon and myself solving Spider by Sabre from the listener. And before that, Listen by Eck, and there will be another listener coming this month, and this month's hard cryptic crossword as well, and the solutions to last month's Patreon reward, well, to October's Patreon reward, are going up these days. So there are those solutions going up for the $3 a month patrons. Do check out Patreon. There's a lot of good stuff there. Connections videos too. And of course, we link to Sven's Sudoku pad under the channel, under the field. Oh, thank you, doorbell. That's very nice. Right, and oh, and yes, while I'm talking about Sven's Sudoku pad, it's worth noting that if you call up this puzzle today and the arrows are obscured by the blue lines, there is a setting for draw arrows above lines, and you need that on if you want to be able to physically see the arrows. I mean, they're fairly clear even if you don't, but that's there. Because for Sudoku pad, it has a lot of variety and a lot of brilliance. Now, there's also, of course, our apps, which feature line Sudoku, arrow Sudoku, domino Sudoku, killer Sudoku, all relevant to today, and Fog of War, and the Worms by none other than Phistomefel, Marty, Sears, Michael Lefkowitz, and today's constructor, James Sinclair. And it's a really good worm, that one. I do recommend it. Now, I think this puzzle is at the harder end of James's difficulty spectre. Spectre? Where did I get that from? Spectrum. That's what I was trying to say. James does also publish his artisanal Sudoku newsletter. Just search for that in Google and you'll be able to track it down. Now, let's have a look at the rules, because these are quite interesting. Firstly, normal Sudoku rules apply, 1 to 9 in every row, column, and 3 by 3 box. But exactly one cell in each row, column, and box. Let's just try finding a possible layout. One cell in each row, column, and box, like this, is a doubler. And doubler cells contain a complete set of the digits 1 to 9. So those ones I've highlighted might be the doubler cells if they were the digits 1 to 9. Now, calm down. A cell's value is equal to its digit, except that a doubler cell may or may not have a value equal to its digit. So imagine this had a 5 in. Its value might be 5 or it might be 10. For the purposes of a clue. The same cell may have different values for the purpose of different clues. I mean, this is mind-blowing. It's a very clever idea. Now, here are the types of lines and cages and things and dots we have in the puzzle. Cages. The sum of the values inside each cage is equal to the number shown. So there, those two cells, their value can add up to 4. Arrows. The sum of the values along an arrow is equal to the value in the connected circle. Region sum lines. Box borders divide each blue line into segments with the same sum, so that one must be equal to those. German whispers. Along a green line, values differ from their neighbours by at least 5, so those two cells would have to be able to have values that differed by at least 5. And purple lines contain a non-repeating set of consecutive values in any order. Meanwhile, for black dots, values in cells joined by a black dot have a ratio where one is double the other. I mean, it's all the normal rules, but they're made absolutely bonkers by this special doubler possibility. Not, I want to call it a doubler technique, but it's only possible that each cell that is a doubler is being used. It's really intriguing. You do give it a try. I'm going to see what we find when we take it on. Let's get cracking. I'm told this, as I said, is a bit harder than James's usuals, and they normally take me plenty of time. So, I mean, the first thing I'm seeing is these ridiculous cells joined by both green and purple lines. So, this is impossible in normal Sudoku, because the green line very specifically says there's a difference of at least 5 between those cells, and a 2-cell purple line says the difference between these 2 cells is 1. And those 2 things can't simultaneously be true. So there must be a doubler on that line, and one on that line. And that doesn't let us, oh, it does let us put some colour in the grid. Okay, what I want to do is colour the doubler cells red and the non-doubler cells green. So I'm going to start by colouring these cells green, because in each case the cell sees one of 2 digits on the line. Like, if that's the doubler, that must be green. If that's the doubler, that must be, etc. Oh, the 4 cage. This is absurd as well. So what you have to consider, I think, with both of these cages is that natural cells, cells with their own digit value, on a purple line, a 2-cell purple line, again, these are consecutive values, and therefore one is odd and one is even, and they add together to give an odd total. So something funky is going on, and one of these is a doubler. So I'm going to red, because these cages have even digits in them as their totals, so they can't be natural in both cases. In fact, what we learn is that in one case, I think that must be true for these lines as well, in one case the doubler is going to be interpreted as double its value, and in the other case, colour of line or cage, the doubler is going to be interpreted as its own value. Now I think this has to be a 1-2 pair. They have to be, the digits have to be able to be interpreted as either consecutive or adding up to 4. And in one case when one of them is doubled. Now I can see that if you double 1 and add 2, that's fine. But if you treat 1 as its natural value and 2, that's fine. That's fine for the line, and the first one is fine for the cage. I don't quite know what the principle is, there's probably some utter principle that explains to me which version has the doubler. I don't understand what it is. I'm just going to look at trial and error, I'm afraid. So, yeah, I mean, it's interesting because you could make up this even total by doubling one digit, doubling an odd digit, and adding to an even number. Obviously, you couldn't make it up by doubling an even digit and adding an odd number. But maybe it's the line that you need to get correct by using the doubler, in which case, I don't quite know how that would work. Oh, the cage would naturally add up to 10. And then you'd double one digit. So it would be made up of 2 odd digits, either 1 9 or 3 7. Yes, actually 3 7 here would add up to 10, but 3 would double to 6. 1 9 I don't think you can make work, but that could be 3 7. But actually it could also be 3 4. Double 3 plus a 4 equals 10. Yeah, it's either 3 7 or 3 4. I don't think this has that optionality because it's too low. But that's really weird. Yeah, 3 7 would work. You'd read them as their natural digits for the cage, and the 3 being doubled for the purple line. But if it's 3 4, you're reading them as one of them being doubled for the cage, the 3, and it's always the 3 being doubled in that cage. It's always the 1 being doubled down here. There's no point doubling the 2 for any purpose. Yeah, okay. So we've found where there's a 1 doubler and a 3 doubler. And look, we've made green cells on 2 of these lines. So their other cell has to be red. And that's huge. That gives us a ton of colouring of green that we can do. We're only allowed 1 red in each row, column and box. And that's coloured most of the grid suddenly. Oh, and this thing now needs a doubler, and there it is. And we get more colouring to do. And now it's about time, you say, that I start thinking about these arrows, which also look pretty weird. Oh, they do look weird. Okay. What's going on this arrow? So in the blue line reading, I don't know, I'm going to, this may be crazy, I'm going to label the letters with digits. Let's say A, B, C. And these are all the same form. There's one cell, the tip of the arrow is in a different box from the other 2 cells. Then there's one cell that is in the next box, and then the circle that's in the next box. So they're all the same. Now, there must be some sort of algebraic formula. So for the blue line, what we've got is A equals B plus C. Oh yes, it's ridiculous. You can't. These can't be genuine both ways. This is the important thing. They can't be genuine both ways because in the arrow variant, C must be bigger than A. But in the region sum line variant, A must be bigger than C. So there is something funky going on with each arrow, and they all need a red cell, and we've only got 1 space left in each of them, and that gives us loads of green in the puzzle. And it's always the circle that is doubling in one version. So in the version where the circle does double, that is going to take the lower value, C, from being lower than A to being higher than A. So in the version where C doubles, 2C, I want to do this as algebra. 2C equals B plus A on the arrow. No, yes, on the arrow you've got B and A, in the circle you've got C, but that's going to be doubled. So I'm putting 2C on the left of my line in the grid and BA on the right. 2C equals B plus A in algebraic terms. For the region sum line version, A equals B plus 1 value of C. So let's put that over here. I'm just using these cells as an aide-memoire. A equals B plus C. Now, what does that mean? Does that mean we can cancel off? The way I always used to do simultaneous equations was by substitution. So what I want to do is rejig this one and say that it means that C equals A minus B. That's what it means, this formula. I mean, you can see that from the region sum line. A is the total of B and C, so C equals A minus B. And then I'm going to substitute that in here. We've got 2C, so that's 2A minus 2B. If I put A's there and B below them, they're minus. And that equals A plus B. So to get 1A, I move that B over here, and it's a third minus. No, hang on. What am I doing? 2A minus 2B. No, I move those 2 B's over here, and they become pluses. 2A equals A plus 3B. Let's remove 1A from each side now. A equals 3B. And let's put that into the top one. We've effectively got 4b equals 2c. So A equals 3b and C equals 2b, or not to be. Right, these are our final equations. A equals 3 lots of B and C equals 2 lots of B. So B is always the smallest digit in the combo. A is 3 times its value and C is twice its value. So one of the possibilities here is 1. 1 with A being 3 times its value and C being twice its value. So that's one possibility. The other one, or the other ones, I think we need 3 different ones. Yeah, these are the 3 possibles because we've gone up to 9, the highest Sudoku digit. So the A digit in all of these arrows can be 3, 6 or 9. So let's write that in. The B digit is 1, 2 or 3. And of course they're all proportional with each other. And the C digit is 2, 4 or 6. So let's get rid of the aide memoir, finally. And these are genuine markings now. And of course, these C's are all different because all the red cells are different because the doubler cells contain a complete set of the digits 1 to 9. And happily, we have found different values from what we found here and here, where we had a doubler 3 and a doubler 1. Now we've got a doubler 2, 4 and 6. The remaining doublers in the puzzle are selected from 5, 7, 8 and 9. Now oh, this cell sees all of these doublers. And it's a black dot cell. Now it can't be 2, 4 or 6 because it sees them all. This one in the row, this one in the row, this one in the box, this one in the column. So this is 1, 3 or 8. And I think we can do better because doesn't it see all the B's as well? It does. That one is in the row, that one's in the box, that one's in the column. And they're a set of 1, 2, 3. So this can't be 1 or 3. And there's our first digit in the puzzle after 12 minutes. A bizarre 8 in the corner, not on a doubler at all. And that needs a 4 on its natural counterpart. And that 4 sees these 2 cells which can't be 4s. And now this one is the doubler 4. And this digit below it is the 2, and this one is the 6, and we can eliminate those from these cells. That is a lovely beginning. My goodness, that's so clever and intricate. Now, just to prove that the maths works here, so for the blue line version, 4 plus 2 equals 6. That's fine, that's normal values. But for the circle version, double 4 equals 2 plus 6. So this does work. Thank goodness for that, because if it didn't, I've been talking absolute nonsense. Now, what else can we do up here? Is there anything else? Those, do they have to have a 3 in? Oh, no, oh my goodness, that's beautiful. Right, there are 2 ways round you could put these arrows. This one could be the 3, 1, 2. And then this would be the 9, 3, 6. Now the reason I know that is going to happen is because the other way round, this would be 9, 3, 6 with a 3 there. And this would be 3, 1, 2 with a 3 in the same box. And they would clash. So that can't happen. So this is the 1, that's the 2, that's the 3. This is the 9, that's the 3, that's the 6. And we're making progress now. We are if I write the right digits in. Sorry, that was meant to be a 1. Mistyping at that point, not helpful. Okay, remaining cells in the top row are 5, 6, 7 and 9. Sudoku might come to our rescue. We've got a 2 down there and a 2 there. One of these 2 is a 2, and I don't think it can be on this because I admit that you could double 2 and get within one of a digit that goes in there. But that's not relevant because this cell is a natural green cell. This is the possible doubler. So we can't put 2 there because we'll never get a Ren band that works out of a natural 2 and a doubled or single 5, 7, 8 or 9. So 2 must go there. There's a 1 in one of those cells. I am going to mark that. Right. This sees these 3 reds. Oh, wait, it actually sees the 4th remaining red as well. So I'm talking about the red that goes in box 7 in one of these cells because we haven't greened them. Somewhere here. And you might suspect it's in the circle, but I don't think that's proven. And remember, it doesn't even have to have its own value. Somewhere here there is a red 5, 7, 8 or 9. And this cell sees, oh no, hang on, does it see that one? It sees that in its column, it sees that in its row, it sees this one in its box. It does actually see this on its line because whether you're interpreting this line as a whisper or a Ren band, these 2 cells can't have the same value. They could if they were both 1s and you were doubling one of them, but the doubled 1 has gone over here, not here. So this cell sees 5, 7, 8 and 9 in a bizarre way on all the red cells remaining. It also sees 3 and 6. So this digit is 1, 2 or 4. But remember, we have to achieve a Ren band here somehow. And with 1, 2 or 4 there and 5, 7, 8, 9 here, or actually 5, 7, 8, 9, 10, 14, 16 or 18 here, still the only combo that achieves a Ren band is 4 there and 5 here. And I'm sure that's right. So these can't be 5s, nor is the red cell in here. It's a 7, 8 or 9. Oh, there's a 2 by Sudoku here. Now, these are going to achieve proper Ren bands too. So these digits must be at least 6 because the values in these cells are either 7, 8, 9, 14, 16 or 18. I mean, this is a weird puzzle to make me say bizarre sentences like that. But there we go. Now, let's look at this arrow. If these have natural... Oh, these all do have natural values. Does it double this? I don't think it does, because this could be a 3-4 pair, and that could be a 1, and that only takes us up to a minimum of 8, and that digit could go in here as a natural, either a natural digit or a red cell using its natural value. So let's forget that arrow. Let's look at this black dot, which isn't a 3-6 black dot. Or this Ren band. Okay, this Ren band, I know one of the digits on it. It is 6. Yes. Oh, look, 9 is looking at that cell. I hadn't seen that. That can't be a 9. Where is 9 in this box? That's a beautiful question. Where is 9 in box 1? Beautiful. By Sudoku, it's not there. It's not allowed on a black dot. These 2 black dot cells are natural values, so you can't put 9 on them, or the other would have to be 4.5 or 18. That is not a 9. If you were to put 9 on this natural value Ren band, the other cells on the Ren band would have to be 8 and 7, and this would be broken. So it's not on the Ren band, it's in the corner. And that's just peculiar. I mean, it's probably not going to do anything else, but it's a lovely deduction. Now, this Ren band does not have 1 or 2 on it, because it doesn't have 3 on it, and it's natural values. So 1 and 2 in the box, 2 is going in one of those cells, but one of 1 or 2 is going to have to get on the black dot, because you can't put them both here. So this black dot is either a 1-2 or a 2-4 pair, and there is a 2 on it, and this 2 is telling us where that 2 is. It's telling us it's there. Now, I don't know whether this is the 1, or, well, 1 is in one of those two, I can't highlight them together, one of those 2 cells, that's what I know. Oh, 3 by Sudoku, I've just noticed, is in one of those 2, and then one of these 2. Is that interesting? 4's in one of those. There is Sudoku to look at here. 6 is in one of those. 2, 1, maybe that's all. Right, let's think about this Renban again. It can't have 8 and 7 on it because this cell would break. So it's not 8, 7, 6. So at the maximum, it's 7, 6, 5. At the minimum, it doesn't have 2 or 3 on, so it's 4, 5, 6. So 5 and 6 are on this Renban, along with 7 or 4. And 8 is not on it, and 8 is therefore in one of these 2 cells. And one of these 3. It's quite complicated concepts, but they are coming together a bit. What next? I still want to attack this thing. Oh, the black dot. What's going on the black dot? Oh gosh, I haven't thought about black dots in this format. How could you ever use a doubler value on the black dot? If you were using a doubler value, the other cell couldn't be half that value, or it would need to have the same digit in it. I suppose it could be double that value. Could you put, oh look, you could put a 2 and an 8 on this dot if you doubled the 2. That's so freaky. It's true though, I think. So these digits, this is either the natural values of the digits, even if one of the cells is coloured red, we're either using the natural values of the digits or we're using 2 and 8 with a doubled 2. So this black dot, which can't have a 4 on it anymore, oh, it can't have 1 and 2 as digits because that would break this cell. Does it now have to be 2 and 8? No, it can be 3 and 6. It either is a 2-8 pair in that order, or it's a 3-6 pair. It's so strange what you have to think about for this. Now, I'm going back to this. I think it can still have 3 and 4 in these cells. And a 1 here. So this doesn't have to be a doubled value yet. Oh, Sudoku, there's a 2 there. That's good. 3, 2, 4, 6, that doesn't do anything, does it? There's a 9 in one of these cells. Thrilling. 3 down here. This is a natural Renban, which doesn't have a 2 or a 5 on it. It can't be, it doesn't have a 3 on it either. So these digits are selected from 6, 7, 8, 9. That one can't be a 9. This is also from 6, 7, 8, 9. Oh, we need a 4 in this row, and that's got to go here. And now there is a 4 in this cage, and it's definitely a 3-4 cage. That's so interesting. Oh, I'm not going to remove the highlight, the corner cell 3, because that's telling me about which one is the doubler. Oh, that 4 is looking at this digit, making it a 1. That 1 is looking at this box, placing 1. It's also looking at this box, putting 1 in one of those, 1 in one of those 2 cells, and that fixes 1 in box 5, and there's a 1 in one of these cells now. We've got a 1 down here. one of these 4 is now a 1. Oh, this digit cannot be a 1 anymore. And that's very important for this arrow. That means that this arrow's minimum sum is 3 and 4 here and a 5 here, which adds up to 12. So this is a doubled cell. It's even using its doubled value on that arrow. And now we can fill in not just that these are green, but also that these 2 are green, and that therefore these 2 are red and are the doublers. And we know we needed a doubled 1 down here and a doubled 3 there to go with 4 and 2 here. Now, that's going to definitely help. It places a 2 here, I think, because I've got that 2 and that 2. So now I've got a 2 on this Renban, which has got to have a 3 on it now, and either a 1 or a 4 in the 3rd position. That can't be a 4, apparently, so it is a 1. There we go. So one of these 2 is a 1 by Sudoku. I mean, I think I'm right. I don't see that I've done anything wrong. This is 7, 8 or 9 getting doubled. So this, which had a minimum value of 12, actually adds up to 14, 16 or 18. Oh, what? These 2 add up to... Oh, no, but they could be adding up to the single value of this digit. Gosh. Oh, there's a 4 on this Renban now by Sudoku. So this is a 4, 5, 6 Renban, and these other 2 cells are 7 and 8. 9, 3, 2, 1, 4 or 6, 5 or 6, 4 or 5, 4, 5 or 6. So one of those is a 4. 4, 8, 6, 3, 2, 1. I'm just trying to work out what this... I think there's a lot of Sudoku to do now, if I can just work it out. 2 down there means this is not a 2, 8 pair. This is a 3, 6 pair. And that 3 is telling us which way round they go. And now, this digit, what about these? Neither of them can be a 3. So the lowest total for those 2, it's not even 4, 6, because that would break this cell. So it's 4, 7, adding up to 11. This one has to be at least a 5. That is a total of 16. This cannot be a doubled 7 anymore. It's either doubled 8 or doubled 9. This digit can't be a 6. I don't know what that does. Is this the only place for 4 in the box? According to the pencil marking, yes it is. Okay, that's a 4 by Sudoku. Right. These 2 either add up to 12 or to 14. There still seems to be... Well, they can't use a 3. And they can't use a 4. So if they added up to 12, it would be a 7-5 pair. If they added up to 14, it could be 9-5, I think. But that's inappropriate, actually, because if they were adding up to 14, that would be a 9, the 18 total. Oh, they could both be 7s and add up to 14, so got to be careful there. But they could also be 8 and 6, which actually is my favoured likely solution. So this is just not resolved, basically. I shouldn't have been spending time on it, it turns out. Right, 1 there has fixed 1 in box 6. That hasn't fixed 6 entirely. 9 is in one of those positions. Oh, should I be doing this still? I don't know. Maybe if you've worked it out, or tell me. Oh no, 6 is looking up at the Renban. So I can place 6 on the Renban there. Then that is not 6. So the even digit here is an 8 on this Renban. And that can't be an 8 anymore. And yet we need a Renban that actually functions here. So this digit can't be a 9 because that is now 6 or 7. It sees 9 there and 8 there. So this is now a 7, 8 red pair, and that digit is a 9. And these two add up to 14, and that's not a 5 anymore. They're either an 8, 6 pair or a 7, 7 pair. Oh, there's an X-wing on 6s. One of those is a 6, and one of these is a 6 by Sudoku. So that rules out that being a 6. It puts 6 in one of these cells. Oh, the 4 has made that a 6. Oh, sorry, it's all much clearer than I realised. That's going to solve some things. This can't be 6. Oh, it can't be 6 now. That's a 7, that's a 7, and this line adds up to 18. That's a 6 by Sudoku. These digits are 5 and 8, and we know the order. And now that can't be 18 on this arrow. It must be 9, and that's got an 8 and a 1. And is that our last 1 being placed in the grid? I think it probably is. And I think we're on track for a finish now, in a very peculiar puzzle, if I may say so. 6 and 9 there. That's a 5. This one is known. That's a 2. Something looked wrong down here to my untrained eye. I don't know what it is. 8 is touching either 7 or 9 for the Renban. And yes, I mean, I don't know if I explained. This is clearly 4 versus 10 on the green line version. This is going to be 16 versus something on the green line version. And this is 14 or 16 versus something low on the green line version. There's no real way for me to know that. That's the 5 in box. Whatever this is, 7, 9 pair, 4, and that's a 3, 8 pair. That has become a 6 ever since we got the 7 at the top. This has to be a 7 to make the Renban have a chance of working. That's fixing 6. This digit, oh no, it doesn't. Oh, it resolves because of that. It doesn't resolve because of the red cells all having to be different. In fact, we've filled in all the red cells now. Hurrah! That's an 8 because it sees a 5 and 7. That's a 5, 7 pair. Got 3, 8, 9 here. That one's a 3. This 2's an 8, 9 pair. This is a 3, 7 pair. We know the order. This digit's 5. 3, 8, 9 here. I don't know the order. I'll do... This is a 9. That's a 7. 5 and 7, 8 and 9. Oh, what a lovely puzzle. Really class from James, just as you would expect. 9 and 3, 8 and 3. And there we go. That is very, very pretty. And that is the solution. A lovely puzzle. Double Entendre by James Sinclair, to whom I recommend you very highly. Do check his stuff out. We'll see you again soon on the channel. Thank you so much for watching. Join us tomorrow. We'll be back with more variant Sudoku. Bye for now.